We are creating an alternative Coca Cola can. However, our Coca Cola can has to be made out of paper and it has to be our own design. The can will have to hold 330 milliliters of Coca Cola and must also be as space efficient as possible for packaging. For our design, we decided to choose a hexagonal prism because it isn't an annoying shape to hold, it has a good grip, it can be manipulated to hold 330 milliliters, and it can be packaged into an organized grid, as shown here. To get the dimensions for our can, we use these calculations shown. Here we are calculating the surface area of the hexagon and timesing it by the height to get our total volume. This is a not to scale net we used to create our can. We faced multiple problems building the can. It took multiple tries to fit the net on an A3 paper. We had to prevent leaks, we had to waterproof the paper, and covering the whole inside with duct tape was difficult. The movie was also long and took a long time to export. Limitations during the build project. Human error. We could have measured or cut something wrong. The websites we gathered information from were assumed to be correct. The duct tape that was stuck inside the cup could have reduced the total volume and changed the shape. We could improve our can by waterproofing the paper by laminating it before assembling the cup. We could also have less corners in our design for less leaks. How efficient is our bottle? Using these calculations shown, we have realized that our can is 3.1 times more space efficient than a normal 330 milliliter Coca Cola can. From these calculations, we can see that our can is times 2.2 cheaper than a normal 3.3 milliliter can. Here is a bar chart showing Coke in accordance to our hexagon can in shipping efficiency and cost to make. Degree of accuracy. When we converted inches into cm, there were decimals. We rounded it to 1 dp because it would fit into the formula easy, and most probably Coca-Cola wouldn't have a machine that would measure 0.604. Cans per container. Each container wouldn't fit an exact number. It usually had 2 or more digits. We rounded it down to the nearest unit because even if you had 0.9 of a can, you wouldn't be able to squeeze the extra 0.1. Using pi. For profits, when we calculated the size of the circle, we rounded all the answers to 2 because that was the same digit as the thickness. We rounded the price of the cans to 2 dp because in dollars you can only go to the max of 2 dps in payments. Can thickness. On the article, there were many different comments on the thickness of the can, and so we averaged it and rounded it to the nearest 0.05 centimeters because it kept it fair. Here are our upper and lower bound calculations. The minimum metal needed for our hexagon can was 0.33 cents, and the maximum was 0.99 cents. The minimum metal needed for the cylinder was 0.73 cents, while the maximum was $2.19. Assumptions. We assume that the prices of aluminum are the same as they were on April 20th. We assume that the thickness of the can is 0.05 centimeters. We assume that each shipping container was 6,058 centimeters in height, 2,438 centimeters in width, and 2,591 centimeters in height. We assume that the duct tape didn't affect the amount of volume in the cups. And also we assumed that the cup did not lose its shape and was perfectly like our design. Our container managed to prevent leaks when filled halfway, but when filled to the brim, it started to leak out of corners after 30 seconds of being full. Reflecting. Yes, our finished design will be practical to sell worldwide because it fits nicely in your hand, is easy to drink from, more space efficient for shipping, and is cheaper than the Coke can to make. If we were to create the design again, we would use laminated paper and fold cut that instead, making the cup waterproof. If we could get a robot to produce and or make our design and use a thinner piece of paper, we could have made the design as accurate as possible.